Yes, here we are. It's the physics video lecture. Physics 203 video lecture 11. We are working on the Kepler problem. Okay, that's about as good as it gets. But on the way there, we have to do some fiddly calculations. So I decided to write down a couple more things. And to help us with that integration. So along the way, that big integral that I had set up last time, we had let u equal 1 over r. We had done that substitution. And if we keep going, we can obtain this integral. This is kind of funny looking because it's such a major expression here. We're going to have du, and we can pull out a constant, and you're going to recognize all these things. 2em L squared plus, and notice this is all just a constant. These are all the parameters. Alpha squared m squared over L to the fourth. So pull that out as a constant, and then in my denominator I have this square root 1 minus big square bracket u minus alpha m over L squared divided by this square root right that we saw before, 2em over L squared plus alpha squared m squared over L to the fourth. Okay, so if you do all your substitutions and keep, yes, and this thing squared. So here's where that inverse cosine is going to come from. You're going to pull that out there. This is 1 minus, that's what I call w squared. You've got yourself an inverse cosine, and then when you put your substitutions back in, you know, this integral was your phi. Inverse cosine equals phi. Then you have your cosine phi and all this stuff pulled out. Okay, so this is that intermediate step in kind of a wild form right here. Okay. So, good. So we have that. And as our result that we've already been working with, we ended up with r equals p over 1 plus e cos theta. So the parameter and the eccentricity are now defined as L squared over m alpha, and this is 1 plus 2e L squared over m alpha squared. So I want you to find these by hook or by crook, and here they are, because we need them to discuss the physics. See, everything's parametrized, and we want to get the transparency and recognize our elliptical orbits and so forth. So this is the Kepler problem. Remember, m was the mass or the reduced mass. This was the from the potential energy. This is the conserved angular momentum. This E is the conserved energy. I'll just write these things down. Alpha from U is equal to minus alpha over R. L equals mr squared phi dot. But L is of course constant. E is the energy, also a constant. So these are our two conserved quantities. And the rest is, and then we have M is, you know, it could just be the mass of a pure central force problem. But from the two-body problem, of course, it was the reduced mass. And since this is the Kepler problem, we've got the reduced mass right there. Good, so now let's discuss these things in terms of what we found last time. So again, we're going to draw our x and y, and of course x is r cos phi, y is r sine of phi, because we're in plane polar coordinates. Yeah, so everything's set up here. Of course, to draw a good ellipse, that's not so easy. Except, in the lecture hall, I have everything necessary. Let's even draw our ellipse with the construction. Let me see if I can go backstage here and find some materials. Okay, we're back. It's all about the one take, no edit. So I have a loop of string here, and let me do a couple of constructions for you. Of course, you know the circle. I'm going to draw it and erase it, but you can construct a nice circle, set of points equidistant from the center here, okay? Radius r, but if I have 2 points, and those are the foci of an ellipse, I can actually draw a perfect ellipse, perfect as you want. So we'll do this until we get one that looks pretty good. So here are the 2 foci. Set of points equidistant from these 2 points in a plane. That gives the geometrical definition of the ellipse. So let's have a go at that. Erase this right here. Here goes. And just note where these were. Those are the 2 foci. Yeah, so what do we see here? Geometrical center is in the middle. One of these foci is where the sun is. I'm going to put them even a little farther apart than this and redraw the ellipse. But it's actually important to notice already the ellipse is very close to a circle. Right, from a distance this looks pretty circular. But we can draw, I'm going to draw a couple more, and you guys are welcome to try this too, right? So here now I put the foci pretty far apart, and we start getting something that looks more elliptical. So there's one focus. There's the other. Yeah, so Kepler's first law is going to be that the orbits of the planets around the sun are ellipses with the sun at one focus. That would be this one. Of course, our planetary orbits are much closer to the circles we were looking at. This could be more of a comet type of orbit. Okay, I'm going to draw one more of these and then label it again, just so you see how that comes about. And for us, the benefit is that we'll have a real elliptical looking ellipse here. So let's go ahead and try this. Leave me room to make some comments over there. So I'll put them apart like so. And do a little bit more. goes. Yes. There is our ellipse. We've got a focus right here, and we've got a focus right here. Okay. So before, when we were doing this, this was our origin. In terms of the dynamics, in terms of the polar form, which is up here, remember we're going to prove that that is an ellipse. We have, maybe I'll use different colors here just for fun. You know, we have our x and our y axis like that. So in terms of our polar form, we don't know about or care about this other focus right here. But I'll leave it in there. But yeah, this was our center of attraction. This was where the sun was and the planets are orbiting there. And now we have these definitions. We had the semi-major axis. We have 2 times A. This direction we have 2 times B. Like that. A is greater than B. So called the semi-major axis. A and the semi-minor axis, B. And now we have these points where when cosine of theta is pi over 2, we just have P and minus P. So we have P here, minus P. And here we had, here we have 1 plus P. Over in this direction, I guess I got to complete this right here. We have 1 minus E. Or negative 1 minus E. Yeah, so we assembled all of these expressions here. And let's see what we had. Important to us was the geometrical center here. And we found that this distance, D, so we have A was equal to 1, was equal to P over 1 minus P squared. B was equal to P over root 1 minus P squared. This D, as I'm calling it, this distance in geometric center was A times E, let me write E times A. E times A. And so, yeah, that's the complete set of these results. And we're going to now discuss Kepler's 3 laws. So I can do everything I need to do just with keeping this information up here on the board. There's our picture. If we took one more color here, we could remind ourselves that there's our angle phi, and there's r. So yeah, the homework was to, for one thing, to do this integral and gain all of these expressions here. And then I did these calculations. And then we also wanted to show that this really is an ellipse. Okay. So now let's keep discussing this thing, and we'll see all the physics come right out of there, out of these formulas up there. So yeah, first you just have all these formulas and their parameters, but you demonstrate these things one by one and it all comes alive. So part of our analysis is to look at the eccentricity. So we have E equals 0 when R equals P, which is constant. So the eccentricity equaling 0 is, of course, the circular orbit. That's a circular orbit. And good, so we have that. if E is equal to 0, we look in its expression. So what I was just talking about, of course, was what's up here. Now we look at this definition of E, and we see that E equals 0 implies for the energy that is minus, right? So 1 plus 2L squared I squared is equal to 0. So we end up with E equals negative m alpha squared over 2L squared. Okay. So what about that? Circular orbit has negative energy. In fact, all the bounded orbits have negative energy. So circular orbit, as well as any other bounded orbit, has negative energy. And all bounded orbits have negative energy. Let's remind ourselves what that means. All bounded orbits. And you see that because we have to have E less than 1. Have E less than 1 and energy less than 0. So where have we seen that before? We've seen it before in the effective potential. And I'm going to go back to the effective potential of R, which was L squared over 2mR squared minus alpha over R. It looked like this, and we had said that at this R sub 0 here, there was an E sub 0. So yeah, you guys want to check this. I could check it right here, right now. But I'll just put it in the homework and leave, just leave room in your notes. Show that minimum of U effective of R, right, takes on this value. Yeah, it's a consistency check. Value of star. Okay. And of course, we're going to have that minimum when U effective prime is equal to 0. But U effective prime is also the force. So we'll also show that not U effective prime, so that U prime, okay, you'll get it out of here though, U prime of R0, since that's the force, that has to be mv squared over R0, right? That's our old centripetal force expression that we learned a long time ago. Well, that had better be consistent here as well. So these are consistency checks in your Kepler problem. You got your local minimum and the effective potential, R sub 0. So those facts should all be consistent. And of course, you'll see that they are. So you can just leave room in your notes and fill it in if you just want to put it there, or write it in your homework as well, write it out. What I'm trying to get you to do is actually go through this problem thoroughly because it's such an important problem, the Kepler problem. Good, so we have that. Let's see how we're doing here. Let's see. Okay. So my next topic, and I'm going to erase this board to do it, is to show Kepler's first, second, and third laws. Now, Kepler's first law is your homework problem, but I'll kind of write it down as well. Okay, so these are the properties of our solution here. So we're satisfied with that. So now we want to prove Kepler's laws. of this whole formalism. So this next thing is Keplers laws. He originally formulated them, Kepler did. Empirically, dynamics had not yet been invented. So now Newton invents dynamics, you got your central force problem, you get these results, and now you have to make sure that Kepler's laws of planetary orbits hold true. But of course, this is much, much more general because it holds true for any central body with an orbiting satellite. Good. So Kepler's laws. The first law is the let's say the orbits are, I'm just going to write it short, the orbits of the planets around the sun are ellipses with the sun at one focus. And what you guys are doing, as I showed last time, is you're turning this thing into, x plus d squared over a squared plus y squared over b squared is equal to 1. Once you've demonstrated that, with a little bit of trig, then we have Kepler's first law. And we could extend it if we know about this hyperbolas and parabolas that are implicit in here as well, but we'll leave it at the ellipses, okay? Good. So what about the second law? The second law is the law of areas. And we could say that the radius vector, which is the line joining the sun and the planet, it sweeps out equal areas in equal times. Sweeps out equal areas in equal times. Actually, there's such a good little construction that goes with that. Why don't I do that again? It's not every day that you get to make some perfect ellipses. So yeah, we'll make this very eccentric, even more so. Here we go. This is more like a comet, but what the heck. So there is a very nicely exaggerated here's our sun. This one we'll do in a different color. Okay, but you saw the construction. So yeah, what about this equal areas and equal times? So we're sweeping out a certain area. So when we're really close to the central body, this area, which I'll shade in blue, represents a certain time, and we'll take that same area way out here, and it's going to be a much smaller area that I'll shade. In fact, I don't have to go to the opposite end here. I could go some later time like out here. And then I'd be shading this part. So those are those areas in equal times. And what that means is that when you're close to the central body, you're moving a lot faster than when you're further away from the central body. So there's the equal areas and equal times. For our planets around the sun, very close to a circular orbit, but say for a comet, Halley's Comet, then this would be close to the sun and then way out of the distance, be going very slow, okay? Good, be that as it may, let's see what we have here. For either of these, we have d area equals 1/2 r times r d phi. is phi construction. That's half base times height of a little triangle. So dA dt is equal to 1/2 r squared d phi dt. Okay. So we have 1/2 r squared, and what is this d phi dt of which we speak? It's right up there, phi dot. So that's L over mr squared, L over mr squared. R squareds cancel, and we're left with L over 2m. Well, the mass is a constant, the angular momentum is a constant, so the rate at which the area is swept out is constant. Okay, and therefore, equal areas and equal times follows directly. So, what's important about this is that Kepler's second law was already implicit in the conservation of angular momentum. But of course, dynamics had not yet been invented when Kepler came up with these laws. But you'll notice we didn't use any of these results up there. Okay? We just used the actual fact that we have an orbit around the central body, and that the angular momentum is conserved. Okay, so equal areas and equal times. And the third law, wouldn't mind having it all on one board, but you can't always get that. I'll rewrite this. dA dt equals L over 2m equals constant. Okay, so now for the third law, we can block this off right here. So the third law is the law of periods. And we're actually going to make use of the second law. So what we do is, everything's up there, yes. We're talking about the period t equals the orbital period. So that's the time it takes to orbit the central body. And actually, let's do this. We're going to have the area, since we were working with this dA dt. So the total area swept out is going to be this integral right here. Integral dA dt. So it's sweeping it out, and when the entire time is the period of going around, you've got the total area there. So now let's evaluate this. We have dA dt, which is just L over 2m. So we have L divided by 2m times t. Simple enough. But the area of an ellipse is pi times a times b. You guys should prove that too. That's a simple little calculation. But the area bounded by an ellipse is pi times a times b, and that equals L over 2m times t. Now we're going to make use of some of these expressions up here. Pi times a. Now the b there is equal to, and you guys will see this, I'm replacing the b with the square root of a. Okay, so I take the square root of a, I almost have b, but then I have to take the square root of p. So p to the 1/2. And that is equal to L over 2m times t. And now you can see what we've got. We have a to the 3/2 power is proportional to the time period. So I'll go right up to here with that. We end up with a to the 3/2 proportional to t squared. There's Kepler's third law. The squares of the periods equal to the 3/2 power of the semi-major axis. Okay. And yeah, I'm going to leave it in this form right here. You can analyze pi and p to the 1/2 further, and but we'll leave it there. Okay, that's fine. So this is Kepler's 3 laws. Okay. So now we have a number of applications. We've, fair and square, we did every step, we haven't left a step out. We have Kepler's 3 laws. And I'll put here area bounded by an ellipse. And if you prove that also out of our formula for an ellipse, out of this one here, you can prove that out of this if you want. With, just x squared over a squared plus y squared over b squared equals 1. Forget the d, and then solve for y in terms of x, do an integration. Regardless, we'll accept that we know that. So we have Kepler's 3 laws, and now there's a lot of other applications once we have this in the central force problem. So we'll be done with this. And I'm not taking them in any special order. But let's see, we have how did Newton find the law of gravity in the first place? Law of gravity. He had help from Kepler. So Kepler's laws were well established. And by the time Newton came around, they were even well established with regard to the moons of Jupiter. Jupiter was a central body, had many moons orbiting it. Of course, Earth has its own moon orbiting it. So Newton did this great generalization of the whole idea of Kepler's laws. And here, I'll put a question mark here. There are 2 ways to talk about this. I'm going to give the short version first, and then we're going to do this: how to determine force law of a central force problem from the orbital equation. So this is actually, these are actually the answer to this here, but there's kind of a quick and dirty version we'll talk about first. So I'll put this in parentheses. So for Newton, you have the first thing that he has to understand is, or that he has to think is that the laws of mechanics as they operate on Earth also operate between the celestial bodies. So the same laws for, say, projectiles versus for planets. Same laws hold for projectiles So a projectile is something that we just throw here. And planets. Okay, see, that's memorable. Same laws hold. So that's the significance of this story with the apple falling on his head, okay? So the apple falls on his head, that's a projectile, and he looks up and sees the moon in the sky. You know, that's a celestial body. Same laws are supposed to hold for both. Okay. But the laws, Newton's laws of motion, say for projectiles, are understood. And so here's what we do. We imagine M1 and M2 as two bodies, and we say that the force has to be proportional to, say, M2. So the force on M2 has to be proportional to M2. Force on M2 proportional to M2 because you know, weight equals M2G if you're on the Earth, right? The weight of an object is mass times G. So in terms of M2 being a projectile, then the force has to be proportional to M2. By Newton's third law, though, you know, the force that one exerts on the other is equal and opposite, okay? So by Newton's third law, F, in fact, I'm just going to call it F here, must also be proportional to M1. So this is like a projectile motion thing with the weight, but then if the projectile motion is, you know, with regard to the attracting body, then the force between the two must be proportional to that one. So F is proportional to M1 times M2. Okay, it's proportional to both of them. Next, we now consider a circular orbit. Just circular orbit as in uniform circular motion. I just erased Kepler's third law. It doesn't matter. But this is where that's going to come in. So now the circular orbit could be a planet around the sun, the moon around the Earth, one of Jupiter's moons. So the next thing here is consider a circular orbit. And let's draw us a nice circular orbit here. And this time we'll have M1 in the middle and our satellite M2. A circular orbit, separation distance R. We know from this situation that the force that we're talking about is equal to M2 V squared over R. Okay? That's just the centripetal force expression. So we've got an M2 and the V is 2 pi radius divided by the period, and we're going to square that, and we have a 1 over R. So M2 V squared over R, and let's just pull out the constants. We've got 4 pi squared M2, they don't concern us. We have R squared over R, so there's an R there. And we have a T squared. But here's where Newton uses Kepler's third law, because he knows that T squared is proportional to R cubed. Right, circular orbit, we just had it on the board there. So that's going to be proportional to four pi squared M2, we've got the R, and we've got the T squared proportional to R cubed. And as you can see, r over r cubed, we get a 1 over r squared law. So that's the quick argument where this comes from. And there's no doubt, in fact, it's very clear that Newton used Kepler's third law repeatedly in these discussions. So, in fact, we have the Principia in our conference room, department conference room. So we've got the proportionality, and we have this proportionality. So now we have gravitational force is proportional to the product of the masses, inversely proportional to r squared. Okay. And you could say this is a guess that it holds true everywhere, and then you can call it universal gravitation. And then you could say you found it by using circular orbits. Now you extend it, solve the Kepler problem the way we just did, and discover circles are just a limiting case, of course, because the ellipses were there all along. Now, so in that sense, this is just an approximation because it is just based on circular orbits. It's also possible to get a rigorous determination of a force law from an actual orbital equation. And that I will go ahead and derive as well. But this is the one you remember, because the derivation I'm going to do for this, is much more involved. Whereas this one just has a handful of ingredients. Okay, projectile motion, Newton's third law, circular motion, and then Kepler's third law. Okay. Let's see how we're doing time-wise. I'll set the other one up then, because that would take more time than we want to spend. But yeah, we'll go ahead and set that up. Yeah, this exact version is actually a very interesting calculation. So this is called the determination of the central force law from the orbital equation. And of course, the example for the orbital equation is r is equal to p over 1 plus p cos p. Right? That's what we mean. So what we do this time is we start with Newton's law of motion in the following form. So m r second derivative is equal to f of r hat, so to speak, r unit vector. So that defines a central force, and what we have to do next is express this in terms of plane polar coordinates. So next, plane polar coordinates, we need the acceleration, we need m m a sub c, or no, m a sub r equals, and we need m a sub phi equals something. Okay. But what we're going to find out from we'll actually write this down in general expressions, but for the central force, there is no acceleration in the phi variable. That's actually 0, because it's a central force, and this is consistent with L being equal constant. So we'll have the expression for L equals constant, namely M R squared B dot equals L equals constant. And over here, we will have the expression for the acceleration in the R variable. So this one, this expression in plane polar coordinates, well, I already wrote that there. But yeah, this expression here is the one that is going to be equal to f of r. And then we'll take a big series of derivatives of this thing and finally end up with an expression for f of r. That's going to take a few steps. The first thing we'll do, I would kind of like to pull this out of a hat, but on the other hand, it would be good to derive it too. So we'll do that. We'll derive that, and then we'll get this determination of the central force. Okay, I'll leave it at this right now, and we'll pick that up next time. See you next time.